Today we're going to start with this new thing called related rates. Essentially, it's going to be implicit differentiation, but within a word problem. So these are going to be a little bit tricky. Related rates, and then something else that we do later on called optimization. Those are probably the two hardest things that we're going to do this year. If you take a Calculus 1 again in college, they're going to be the two hardest things you do in the Calculus 1 course. So just kind of be prepared. Yes, this is going to be complicated. Yes, it's probably going to be confusing. But hopefully the videos help. Hopefully the notes keys and the homework keys that I have posted, hopefully they help. Because this probably isn't going to be easy, but we'll see. All right, so they're like implicit differentiation questions, but within the confines of a word problem. Let's jump into it. The first one's not really even that much of a word problem. It's pretty much just straight, bare bones, just the math. Let's look. It says, suppose y equals 5x squared minus 6x plus 2. Find dy dt when x equals 4, given that dx dt equals 2 when x equals 4. This seems really complicated. It gives you this equation. It's got x's and y's. It's defined explicitly, which is nice. But then it says find dy dt. And then it says, okay, at this moment when x equals 4, I know the dy dt. The dy dt is what I'm going to try to solve for. All right, so the dy dt is what I'm solving for, and it gives me this extra fact that, hey, when x equals 4, the dx dt is 2, right? X and y are variables. They're going to be changing. And here, what it wants us to do, if you notice, it wants us to take the derivative with respect to t. So going back to kind of what we did at the beginning of this notes packet, at the very start of the implicit differentiation stuff, we can take the derivative with any variable, and the whole idea is it doesn't really matter which variables you have in your question, and it doesn't really matter which one we're going to do the derivative with. The whole idea is that if the variables don't match, then you need to do chain rule. You d something over d something else. The variable that goes in the top was the variable that was in my term to begin with, and then the one that goes in the bottom is the variable we are taking the derivative with, right? So here we have x's and y's. We're going to take the derivative with respect to t. And a lot of the time, for these related rates, for a lot of the time, we are going to be differentiating with respect to t. We're going to see how do these variables change in regards to time. Okay, so here we got x's and y's. We're going to take the derivative with t's. How do you know? It kind of tells you in the question, right? Look at the denominator, dt. So I have to take that original equation, take the derivative with respect to t, and then it's going to tell me at some point I'm going to plug in x is 4, and then at some point also I'm going to plug in the dx dt, or the x prime if you want. That's going to be plugged in as 2. Let's do it. Let's take the derivative with respect to t. Now, the derivative of y is just 1. But since that chunk is y's and you're taking the derivative of t's, our derivative would be dy dt, or 1 dy dt. The derivative of 5x squared would be 10x, but x does not match t, so I'm going to need to do chain rule, times dx dt. And then it's going to be minus 6 dx dt. And then plus 2 goes away, right? The derivative of 2 is 0. So I take the derivative with respect to t, noticing that, hey, I had x's and y's, so I'm going to need to do chain rule for basically every part. And now, hopefully, when I've done taking this derivative, hopefully I can plug in a lot of values. And then hopefully there's only one thing that I don't know, because I can't solve an equation if there's multiple missing pieces. So I'm going to plug in what I know and hopefully solve for the one thing that I don't know. Let's go for it. Now this derivative, right, isn't always the same thing. dy dt isn't always the same value. So it's important that, hey, we're trying to solve for dy dt when x is 4, and then the other information that it gives me is also when x is 4, right? We're always going to be investigating the same moment in time, or that same specific instant. So here we need to plug in 4 for the x value. So let's go for it. We're trying to solve for dy dt, so of course I don't know that one yet. But for the x value, I can plug in 4 minus 6. And then I also need to be able to plug in something for the dx dt. But the question handed it to me, right? The dx dt I could plug in at that one moment is 2. Now, if you were to look at something like x equals 10, yeah, the dx dt may not be 2 anymore. So everything's got to be kind of localized around that one instant, that one specific value, which here it was, right? We were given information about x equals 4, and then we were asked for other information about that same moment when x is 4. So that's nice. Take the derivative, plug in all the stuff that you know, solve for the one thing that I don't know. Okay, here we go. 4 times 2 is 8. 8 times 10 would be 80. 6 times 2 would be 12. 80 minus 12 is looking like a 68. So there we go. We got dy dt, the instantaneous rate of change of the variable y with respect to the variable t. Looks like dy dt is going to be 68. And that's only at the moment when x equals 4. dy dt is not always the same, right? It's a variable. It's going to change. But at that one instant, when the x is 4, and also the dx dt at that instant is 2, but at that one instant, your dy dt is going to be 68. Now, if you want to use, for dy dt, if you want to use y prime, and for dx dt, if you want to use x prime, that's okay. And a lot of the times you'll see that when I'm working on the homework keys, you'll see the prime notations. You would just need to remember that, like this dy dt, that is not the slope of the graph. The slope of the graph at any point, that is only ever going to be given by dy dx, right? Slope is rise over run. It's the y value over the x value. Dy dt you could still write as the derivative of y, and then you would just have to remember that, hey, you were doing the derivative with t's. So you can do the prime notation as long as you're kind of keeping track of what variable is in the denominator, and you wouldn't want to use that y prime, if it's dy dt, you would not want to use that for the slope of the graph. dy dx is the only slope of the graph. All these other things are just rates of change. How does the change in t correspondingly affect the change in y, right? How are these variables related to each other? But the only one that tells me the slope of the graph, that's only dy dx. But you could use y prime, you could use x prime, you could use these other primes if you want, or you can use the dt notation, whatever. All right, so we're done with the first one. That one's not too bad. It wasn't really even a word problem. It was just straight up math. Here's an equation. Take the derivative. Tells you what variable to take the derivative with. Also gives you some information to plug in. Plug in all the stuff that you know. Solve for the one thing that you don't know. Let's move on to the next one. A pebble is dropped into a calm pond, causing ripples in the shape of concentric circles. The radius of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, find the rate at which the area of the disturbed water is changing. Okay, so think about this, right? I always like to draw a picture. You drop this pebble, it creates this little ripple. That ripple starts small, and then it's going to grow, right? Of course, it says we have these ripples that are in the shape of concentric circles. Of course, that circle has a radius, and then that radius is changing. So we're thinking about the different kind of variables in this question and whether they're going to be static, constant, or whether they're going to be variable, changing. If I drop that pebble, right, obviously it's going to start with a small little ripple, and then that ripple, it says, is just going to keep growing, growing, growing. And it actually tells you what the rate of that ripple is changing at, right? It says the radius is increasing at a rate of 1 foot per second. So the radius rate, right, the rate of change of the radius, dRdt, that's 1. And then if you want to put your units, foot per second. Okay, and then it says at this one moment when the radius is 4 feet, so we're going to investigate the instant when r equals 4. Let's figure out what it wants me to solve for. Find the rate at which the area is changing. So somehow I need to figure out the area, and then from the area, I'm going to take the derivative, and then that's how I can get to the rate of change of the area, right? So if it asks for the rate of the area, you're going to have to start with the area function, and then you're going to have to take the derivative of that area function with respect to t, and then try to figure out what is dA dt, right? What is the area of a circle? We should know that. It's just pi r squared. Okay, so that's pretty good. There's my area of a circle. Let's take the derivative with respect to t. So the derivative of a would be dA dt, or if you want to use a prime, that's okay. But the derivative here on the right side would be 2 pi r times dr dt. Remember to do chain rule because you have r's and you're doing the derivative of t's. So remember to do chain rule when the variables don't match. Now let's plug in what we know and solve for the one thing that we don't know. I don't know the dAdt yet. That's what we're trying to solve for. So that's okay that it's missing. 2 is 2, pi is pi. At this one momentary instant, I'm investigating when the radius is 4. So I can plug in 4 for the r value. And then let's see, what was the dr dt? The question told me it was 1. So then it looks like your dAdt is going to end up being 8 pi. And let's think about what the units would be. You would need the units for area divided by the units for time, where your straight line distance was in feet, and area is two-dimensional, so it should be feet squared, and then your units for time was in seconds. If it's something like the rate of change of the radius, or it's something like the circumference, if it's a straight line distance, then it should only be a one-dimensional distance. If it's an area, you should have a distance unit squared, or if it's a volume, you should have a distance unit cubed, right? So always make sure you're getting the right units, and the differential here tells you really what units are. Units for the area divided by units for the time. All right, so here's an important thing. I know eventually I was going to plug in the r is 4, but you can't do that right away, right? If you plug in the 4 at the beginning, 4 squared, so you'd have area equals 16 pi. If you try to take the derivative after you plug in the 4, you're going to get 0. And that doesn't make sense, right? Think about it. As you drop that pebble, and that circle's growing, you're going to tell me that the area isn't changing? No, that's nonsense, right? Of course it's changing. And I want to know how fast it's changing, right, in regards to time. So at some point, you're going to plug in this r value is 4, but you must take the derivative first. If you plug in the constant before you take the derivative, you're going to actually lose that variable, right? When you plug it in, it becomes a number, and then when you take the derivative of the number, it just goes away and it becomes 0. So yes, these questions, a lot of the times you're going to end up plugging in numbers for the variables, but you must take the derivative first, and then you could plug it in. Right? Don't plug in stuff before the derivative. If you do, you're going to be losing variables, and that just doesn't make sense. All right, so be careful. Take the derivative first, then you plug in all those values from that moment that you're investigating. Like, hey, at that moment, the r was 4, and at that moment, the rate of change, the dr dt, the r prime, was 1. So after you take the derivative, then you could plug in some stuff. All right, let's move on to the next one, which is going to be probably a little bit harder. Okay, here's some area formulas and some volume formulas. I think they're all volumes in a surface area, right? So here's some geometric formulas that hopefully you know. You probably really should know all these. That was kind of the whole point of geometry, so that you would know some stuff when it comes up later on down the road. So if you don't know any of these, you probably would want to commit them to memory. If it's any weirder shape, like if it's a triangular prism, or if it's a rectangular prism, or if it's a square pyramid, those weirder area formulas, like the surface area of a pyramid, or the lateral area of, I don't know, a cone. If it's something weird, they will probably give you the formula. But if it's just a volume, I doubt it. Or if it's just a surface area of a sphere or of a cube, or really even of a cylinder, no, they're probably not going to give you those. If it's a weirder shape, or if it's a weirder kind of measurement of an easy shape, if it's something weird, they will probably give you the formula. But if it's just a basic volume, or if it's a surface area for a very easy shape, you're going to need to know those formulas, right? So hopefully you remember some geometry. Anyway, we got a cone. By the way, pyramids and cones, they would be the same thing. This is except of course for the pyramid, you wouldn't have this. I guess for the pyramid, it would be like the sphere, except it'd just be a 1/3. Anyways, the pyramids and the cones, it's just a 1/3 of your volume, right? So pyramid would be 1/3 of your prism. It's kind of a little bit weird to think about, but just remember, cones and pyramids, those are both 1/3. The pyramids don't really come up very often. The cones do, though. They're pretty nice. All right, anyways, enough talk. Hopefully you know your geometry. If not, you probably will by the end of this unit. Water runs out of a conical tank, so it's the shape of a cone, at a constant rate of 2 cubic feet per minute. The radius at the top of the tank is 5 feet, and the height of the tank is 10 feet. How fast is the water level sinking when the water is 4 feet deep? You're like, Mr. Bell, I don't even freaking know where to begin, because this is a weird question. Okay, that's all right. Just draw a picture. Draw a picture, try to label all the stuff that's going on in this question, and that's a lot of times a good place to start. Let's draw ourselves a cone. Now, be careful. My artistic skills are very limited. There's a cone, and inside of this cone, we've got some water, right? So I'm going to do the water in blue. Hopefully it comes up. Okay, so I've got this conical tank, and then within the tank, I've got this conical shape of water. Now, I'm going to call the radius of the tank, I'm going to call that capital R. And then I'm going to call the height of the tank capital H. And then how about the radius of the cylinder of water? I'm going to call that little r. And then how about the height for that cylinder of water? I'm going to call it little h. So the big capital letters, those are the dimensions of the tank. The lowercase letters, those are going to be the dimensions of your volume or of your shape of water. And now we have this tank, and it tells me water is running out. So I've got some leak or something, but I've got an outflow of water. So as this water is leaking out of the tank, think about visually what's going to happen. It might have started full, we don't know. But as water leaks out, right, this water level is going to go down and down and down, right? You can just visualize water leaking out of that tank. That means this height, as water leaks out, that height is going to be changing, right? And it's going to be getting smaller. But since that height is changing, we're potentially going to be worried about a dH/dt, right? That height is a variable, it's going to change. As that water flows out, also this radius, right? Think about, as the height goes down, that cylinder is going to get narrower and narrower and narrower. So that little r is also going to be changing. So as that water leaks out, the height of that water is going to be decreasing, and then also the radius of that cone of water is going to also be getting smaller. Right, so the little r is a variable, it's going to change. The little h is a variable, it's going to change. So I'm kind of just writing down all the things that may potentially come into play. And let's look at this outflow. It says 2 cubic feet, so it says feet cubed per minute. Think about the units and then what it's telling you that this number 2 really is, right? Feet cubed, so that's a volume. And then minutes, that's per time. You've got a volume over time. So that's really giving you the derivative of the volume, right? So the outflow, that rate of water going out of the tank, that's your dV dt. And also think about it like this. The amount of water in your tank, is that amount getting bigger or is that amount getting smaller? Well, if water is flowing out of the tank, then that water, right, the volume of water in the tank, that volume should be decreasing. So really, I would want this dV dt not to be a positive 2. I would want the dV dt to be a negative 2. You can kind of deal with the negative in a couple of different ways. I would just think, is the volume getting bigger or is it getting smaller? Well, here that volume is flowing out, or that water is flowing out, so that volume should be decreasing. So it makes sense for the dV dt, the rate of change of the volume, it makes sense for it to be negative. You're just not, like, you could count it as positive and then bring the negative in later. I just think it's just easier to put the negative in at the beginning. So anyways, we have this conical tank, we have the cone of water inside the tank. We know as the water flows out, which is the dV dt, that height is going to be decreasing, so it's going to have a derivative that we maybe are worried about. And then also that radius is going to be decreasing, so it maybe has a rate that we're worried about. Let's look at the shapes though, right? The capital R. As the water flows out of the tank, would the capital R change? Is there potentially a d capital R dt? Is there anything like that I'm going to worry about? No. The big R is just the physical dimension of that tank. So that's not going to change. As the water flows out, that capital R, the shape of the tank, it stays the same. So we can label what those are. It says the radius at the top is 5. And then it says this capital H, the height of the tank, that was 10. Right, and those dimensions aren't going to change, so you don't have to worry about their rates. Now the little r and the little h, yes, as the water flows out, that cone of water gets smaller, so those variables, the r and the h, those little lowercase variables, they change, so they potentially have derivatives that you're concerned with, but the capital letters don't, right? The static dimensions of the tank do not change, so you don't have to worry about the derivatives. their derivatives would just be 0. Okay, sorry. Let's go ahead then, and let's try to figure out what other things this question gives me. It says, okay, 2 feet across the top. Oh no, we got the 2 feet growing out. That's good. We got the radius at the top, which is 5. Okay, sorry, I'm back. Sorry, I had to drink some water. My throat was just not having it. Okay, so let's see what else. We got the dimensions labeled. The height is 10. That's good. The radius is 5. We got that labeled. Now it says, how fast is the water level sinking when the water is 4 feet deep? Okay, the water being 4 feet deep, that's your little h value, right? The height of the water is going to be 4. And then it's really looking for how fast is the water level sinking. So it's really looking for, right, as that water flows out, the water level is the dH dt. So it gives me some information about the lowercase h, and then it is wanting me to answer something about the little h dt. Okay, so that's good. I really don't know anything about the radius, and I don't really care about the drdt, the little one. I'm really focused more on the height and then the rate of change of the height. So that's nice. Okay, now the trick for this, let's think about it. If I know the dV/dt, if I know the rate of change of the volume, then you probably want to start with the volume equation. Like a lot of the times you just have to logically think about what you know and what you can work with. And if I have the rate of change of the volume, you probably need to start with a volume equation and then at some point take the derivative to get to the dV/dt, right? So let's think. The volume of a cone, we have it right here at the bottom. It's 1/3 pi r squared times h. Now, you could take the derivative right now. You shouldn't, and I'm going to explain why, but you could, right? You're able to take this derivative. If you wanted to, you could take the derivative. The derivative of v is just v prime, or dv dt. Let's see, that's just all a coefficient, so I'm just going to copy that out in the front. But if I had r squared times h, you would need to do product rule. The derivative of the first would be 2r dr dt times the second, plus the derivative of the second times the first. You could take the derivative right now. It would involve product rule, but in theory, product rule is something we should be able to do. But the issue isn't really that I couldn't take the derivative. The issue is that if I took the derivative right now, there would be too many missing things. Let's think about what we're trying to solve for and what I could plug in. The dV/dt, I know, right? It was the -2. Obviously, the 1/3 and the pi, those are just constants. The 2 is a constant. The radius is fine. I know, actually, no, we don't know what the radius is. We could find it, but that's just creating a problem to answer a problem. I don't know what the r prime is. I know the h at that instant we were going to plug in was 4. And then the h prime, that's the thing I'm looking for, so that's good. Ooh, and I also don't know the r. So I don't know the r's, and I don't know the r prime. Could I find those values? Yes. But then you're creating a question to answer this question, and you're kind of just not getting to the answer in the quickest way possible, right? You could figure out what the r's are, and then afterwards you could get the dr/dt, but then that's just not as super efficient. Okay, so what we'd really want to do is somehow, instead of having both r's and h's, which, I mean, calculus-wise is okay, because we could take the derivative, which is going to have r's and h's. We'd have to do product rule. That's okay. And if I knew all of the information, if I knew what the r was, and if I knew what the dr/dt was, then yeah, I would have taken the derivative, and I would just plug in everything, and I would solve for the one missing piece. But right now, since I don't really know anything about the r's, I kind of want to get rid of them. I kind of only want to have h's. All right, so knowing when to take the derivative is sometimes a struggle. Here, you could take the derivative, but you would get stuck because you're missing too many things, right? You can't solve an equation if you've got 1, 2, 3 unknowns. So what we want to somehow do is narrow this down and whittle it down so that we only have stuff that we know, right? And we know stuff about the height, and we know stuff, or we want to know stuff about the rate of change of the height. So if somehow I could get rid of the r, that would be wonderful. And here's how that's going to be done. Think about this geometrically. I have this cone of the tank, and then I also have this cone of the water. They share that same common vertex. So those are similar figures, right? Similar figures. And this key is going to be important. That's how we really do. Anytime you've got a tank situation with stuff inside of the tank, it's always going to come down to a proportion from these similar figures where we can set up some ratios. Here we go. I'm going to do big R over little a, big R over big, right? You could do big R over little r and then big H, little h, or you could do big to big, little to little. It doesn't really matter as long as you're consistent. I'm going to do the big radius over the big height. That's going to have to be proportional to the little r over the little h. Since they are similar figures, they are going to be proportional. So I could set up these ratios that are equal to each other. There are other things you could do, like you could do r over r equals h over h, as long as the capitals are on top or the capitals are both on bottom, right? There's different ways to do it. I usually just do big over big and then small over small, making sure you get the same orders in each one. But you need to set up a proportion based on similar figures. Then I can cross multiply. Actually, no, what we'd want to do is plug in some stuff, right? You could cross multiply now, but I'm going to actually plug it in. The big radius, that never changes, so you can plug it in. The big height, that never changes, so you could plug it in. Do not plug in these, right? Those are variables, they change. And remember, if there's a value that changes, you've got to take the derivative first before you plug it in. We talked about that in the previous example. So here, this ratio, 1 over 2, that reduces, so your r over h ratio, it's going to be 1/2. So like if you knew the height was 4, then you could easily tell me that the radius is 2. And once you know the radius is 2, like you could come back and you could plug it in here, and you would still be missing the r prime. There would still be ways to work around it, but it's like, why? If I can just get rid of the stinking r's and work only with h's, my life is going to be so much better. Right? So I set up the proportion, I plugged in the static dimensions, the things that never change. Do not plug in anything there. And then I'm going to do my cross multiplication. So h is going to be equal to r. The height is always twice as big. So that means your radius is h over 2. Right, so I set up this proportion based on the similar figures. I plugged in the ones that never change, cross multiplied, and now I could take this expression for r, and then I'm going to actually come and plug it in, and I'm going to substitute away that r. So I have my volume, which is 1/3 pi, and then instead of the r, I'm going to change it to h over 2. And now look at that, right? Now I've kind of whittled it down, and instead of having r's and h's, now I've just got h's. I mean, I still have the v, but that's okay. We know what v prime is. Before you take the derivative, which you could, right? You'd have to just do chain rule here, and you'd have to do product rule. I would just suggest simplify first before you take the derivative. So you have 1/3 pi, that's h squared over 4 times h. So here we go. We got 3 and a 4, so I've got pi over 12, and then h cubed. There is your volume equation based only on the variable h, right? You could have taken the derivative here, but since you have r's and h's, if you took the derivative, your derivative would have r primes and h primes, and you don't know what that is. You could go ahead and find it, but then you're creating extra work for yourself. So if your function has r's and h's, the derivative would have r primes and h primes. I didn't really want that since I'd be missing both of those things. So somehow I needed to algebraically figure out how I could get rid of one of those variables. And since r was the one I didn't know about, that was the one I wanted to get rid of. And the trick to do that was to set up the proportion with your similar figures and then make a substitution to get rid of your r. And then after you do the substitution, probably still shouldn't do the calculus. Simplify it first, and then finally, now, we're ready to do calculus. Right? This is scary, but we haven't done any calculus yet. The one calculus step in this whole question is right now, when I take the derivative. Everything else is logic, it's geometry, and it's algebra. Okay, so the thing that makes these related rates questions hard isn't the calculus. It's all the stuff you're supposed to know from the previous 3-4 years of your life, and it's all the ability of thinking through these kind of weird word problems. The calculus is just taking a derivative. That's the easiest step. It's everything else that's hard. But hopefully the more we do, the better we'll get. All right, take the derivative with respect to t. So here we go, dv dt, or if you want to do v prime, that's fine. But there's your derivative on the left. Let's see. This 3 is going to multiply, so you'd have a 3 pi over 12, so that's just going to be pi over 4 h squared times your dH dt. Again, you could do V prime and H prime if you want. A lot of the times you'll see that on my homework. I like the prime notation because I'm lazy. It's a little bit less writing. But here we go. We finally got the volume down. So that was just V's and H's. Take the derivative. So I have a V prime and I have an H prime. This is fine because we know what the V prime was. It was -2. Pi over 4, just plug it in. Now that I've taken the derivative, now I can plug in the 4 value. And then your dH dt, that's the one thing that we don't know. So that's what we're solving for. Okay, so very good. Let's see. That 4 is going to cancel one of those. So I've got a -2 equals 4 pi times dH dt. Am I still on the screen? Yep. Divide all this over. And then we can just reduce it. Here we go. dH dt is going to be equal to -1 over 2 pi. And then don't forget your units. I would need the units for the height, which would be feet, and then your units for your time, which would be, I think, minutes for this question. Always be careful for your units. Height is just one-dimensional. If it was an area, it would be a feet squared. If it was volume, it would be a feet cubed. That's kind of how you knew this one was the cubic, right? Because cubic means that was the rate of change of the volume. But here, since it's just a height, just one-dimensional. All right, so that's the answer. Let's think, does the negative make sense? As that water flows out, is the height going to be increasing or decreasing? Well, as the water flows out, the height's getting smaller. So yes, the derivative should be negative, right? That makes sense. So there you have it. Your dH dt is equal to -1 over 2 pi feet per minute. Now, again, it's just like there never ends to be like all these problems and tricks with these questions. This is a perfectly fine answer. If you were to say dH dt equals -1 over 2 pi feet per minute, that's fine. dH dt is equal, and it should be negative because h is decreasing. Let's read the question, though. It says, how fast is the water level sinking when the water is 4 feet deep? Okay, if this was a multiple choice question, one of the answers would be 1 over 2 pi. Another answer would be -1 over 2 pi. And then the other two answers, I don't know, C and D, they would be clearly wrong. If this was a multiple choice answer or a multiple choice question, the answer would not be the negative value. It would be the positive value. And you just think about kind of the logic behind it. It says, how fast is the water level sinking? If you said the water level is sinking at a negative rate, see that double negative? That actually means the water level would be getting bigger, right? If it's sinking at a negative rate, then that actually means the height would be getting larger. You would just say, hey, it's sinking at this rate, right? Now, dH dt is negative because h is decreasing, but dH dt doesn't necessarily imply sinking or getting bigger, right? But here, if you were to say sinking at, really the sinking, that word is the negative sign, right? It's sinking at this rate. If you were to say it's sinking at this negative rate, the two negatives would cancel. So again, just kind of be careful. This is a fine answer. dH dt is the negative value. But then if you wanted to actually write out a sentence, or if it was a multiple choice answer, it would be sinking at the positive rate. Hopefully that makes sense. Again, it's kind of ticky-tacky. Most of the time, it's going to be pretty obvious whether you want the positive or whether you want the negative. Just always read it back to yourself when you're done and think, does it make sense to be positive or should it be negative? Okay, if it was sinking at a negative rate, that would actually mean that tank is filling up. It should be sinking at a positive rate. That means the height would be going down. Okay, I'm going to pause it here. I know 34 minutes for 3 questions. I'm going to flip it over to the next page and do the next couple of examples in the next video.